on air.
Okay, next up we have Bodo Schwabe from University of Göttingen telling us today about galactic scale fuzzy dark matter.
Cool, thanks, Philip. Yeah, today I will talk about fuzzy dark matter on these galactic scales, so on nonlinear scales. And now the slides work. So just to give you a brief introduction, fuzzy dark matter as a non-relativistic self-gravitating scalar field is by definition evolved by the Schrödinger equation in combination with the Poisson equation for its self-gravitational potential. And therefore, even though it's a classical field, it has all these wave-like phenomena on the de Broglie wavelength scale, so a length scale proportional to 1 over the velocity. And then there's also typical time scale, which is just the inverse of the velocity square of our specific problem. So that's the important length and time scales. And then there are basically 2 main distinguishing features between fuzzy and cold dark matter. The first one, namely on linear scales, is the initial cutoff in the power spectrum. And that can be analyzed by linear probes. I will come to that on the next slide. But then even more interesting, I think, on this de Broglie wavelength scale, so on this typical scale of that problem, we see these interference patterns due to different wave vectors or plane waves that interfere. So as we see here, these are the results of this landmark Nature paper already 6 years ago by Schwabe et al. And here on the left, we see that on large scales, on linear scales, cold dark matter and dark matter here is fuzzy dark matter. It's really indistinguishable on those scales. But as soon as we zoom into filaments and halos, where we have velocity dispersion and therefore interference in the fuzzy dark matter part, then we here clearly see different characteristic phenomena for fuzzy dark matter. And that basically results then in these typical radially averaged density profiles where as soon as we average over multiple de Broglie wavelengths, so in this outer halo part, we have the traditional NFW profile, but then in the center of each halo, typically a soliton or solitonic core or boson star forms, so a ground state solution of the Schrödinger Poisson system. And these you can see here in the lower left panel at the left part, so in the central region of each halo. So this is just to cover the linear scales. So as I said, on linear scales, we have this initial cutoff in the power spectrum, and that can be probed by the CMB and large scale structure, reionization, UV luminosity function, and then also the weakly nonlinear regime by Lyman alpha. But those scales are only interesting for very light masses. So masses below 10 to the minus 22. These really then the cutoff scale is so large that it can be actually probed by these linear probes. But as soon as we have slightly heavier masses, then this scale becomes so small that it's in the nonlinear regime, and then we start to need dedicated fuzzy dark matter simulations for these nonlinear behaviors in collapsing structures like filaments and halos. So here I will be mainly concerned with simulating those mass scales around 10 to the minus 20. So this small open gap here that is then from the heavier mass side, then constrained by black hole superradiance phenomenology. So in this mass range here, 10 to the minus 20, we assume a typical velocity of 100 kilometers per second, and that would result on to a Boy wavelength of 10 to 100 parsecs. So we really talk here about galactic scales. So today I want to basically quantify then fuzzy dark matter dynamics in especially in halos, and we'll have a look at radial density profiles, at the equivalence between cold dark matter velocity dispersion and fuzzy dark matter granular structure, so this interference pattern on the Boy wavelengths, and then also the solitonic core dynamics. And I will do that in 3 different scenarios, namely for pure fuzzy dark matter, for fuzzy dark matter and baryons, and now for the first time I will show results for a mixed dark matter case with fuzzy dark matter and cold dark matter alongside each other with varying fractions. And I will do these things or these simulations using adaptive mesh refinement. Then I introduce a hybrid method both with particles and grid method, finite differencing, spectral methods, and n-body methods. So basically the entire range of algorithms that are typically used. So let's start with a pure fuzzy dark matter case and the hybrid method. And here you can see our typical simulation that we did 3 years ago, I think, where the large scale structure that you can see here in the background is evolved by n-body particles. And therefore, we assume that on these scales, fuzzy dark matter is equivalent to cold dark matter. But then we focus on a specific halo, namely the one that you can see here in the middle. And we strongly refine that. And then on the most refined level, we use a finite difference grid-based method and evolve it there with finite differencing. And here, the result you can see here in this inlay, we see the granular structure in blue, and then the solitonic core in the center in orange. So how did we construct this hybrid method? So the goal was adaptive mesh refinement, basically saying we want this huge volume, but only need a small region to be refined. So therefore we use adaptive mesh refinement for that. We have a particle method on the volume filling huge simulation box, and finite difference on only on the finest level. And then the tricky part is really the boundary conditions between these 2 methods, where we have both a spatial boundary between different levels and also a temporal boundary, in the sense that in the initial collapse is completely done by n-body particles, and then only once we enter the slightly weakly nonlinear regime, we start to introduce the finite difference method. So there's also an initial conditions problem here. So how we do this reconstruction? We do that by using the Madelung transformation. So basically representing the complex field. So this wave function in polar coordinates. And if you then plug that into the Schrödinger equation, you obtain the Euler equations with an additional term that's typically called quantum pressure or gradient energy. So we use that representation and associate the particle velocity with the gradient of the phase, or the complex phase of the wave function. And therefore we can initialize the phase by using that the divergence of the velocity is proportional to the Laplace operator of the phase, and then use the Poisson solver of our code. In this case, we used ENSO to reconstruct the initial phase. For that, and then this initial phase is given to the n-body particles and evolved in time by this phase evolution. So n-body particles are now not only containing their phase space position and mass, but also this additional information of their phase, and it's evolved alongside their trajectories in the phase space. And then at each point where we want to reconstruct the wave function, we do that by reconstructing the phase by this lower equation here. We basically average over all particle phases around a certain grid. And also the amplitude is constructed as the square root of this averaged density obtained by cloud and cell method. So we each particle is associated to a kernel, and then we put those kernels on a, or sum up those kernels on a grid, and then the square root of that classical density we use as the amplitude. So it's a classical density, therefore we don't have gradient energy, and therefore we also don't have interference effects and interference patterns. So we really have to make sure that we reconstruct the wave function far enough away from the halo, so that interference is negligible. Yeah, and we ran those kind of simulation, and that's basically the results that can be looked up in this paper reference here. And what we mainly found is that you can take this wave function, this interfering wave function, Fourier transform it, and take the absolute square, and the resulting velocity spectrum that you obtain, you can see here in this upper left panel, and it's very nicely parameterized by a Maxwellian shape. And interestingly, we reran the exact same simulation with pure n-body particles, so basically cold dark matter simulation, and had a look at that velocity spectrum from the particles. And as you can see here in this upper left panel, it's apart from small numerical deviations, it's very much the same. So that shows that the so-called Schrödinger-Vlasov correspondence indeed holds. So that basically quantifies that cold dark matter and fuzzy dark matter is indistinguishable on super de Broglie wavelength scales, not only in the densities or in the position space with looking at the densities, but also in momentum space looking at the velocity distributions. And then we also had a look at the survival time of these of different granules, and what we saw is that they fluctuate on indeed on this de Broglie timescale, so 1 over velocity squared. And on the lower right panel, you can see that all these granules are not self supported by their own gravity, and therefore variate rapidly on that de Broglie timescale. And only the central granule, so this ground state soliton solution, is indeed virialized and self-supported by its own gravity. And finally, we had a closer look at that ground state solution in the center. And here on the upper right panel at the top, we show the central density, and you can see it oscillates. And therefore, we took the temporal power spectrum of that and had a look at frequencies, and we recover this characteristic frequency that we can indeed identify as the quasi-normal mode of that soliton, which rings on the freefall time scale, so on the characteristic time scale of that ground state. So that was the first case, pure fuzzy dark matter. And as a next step, last year, we then included baryons as well to make these kind of simulations more realistic. And basically with baryons, we did the same kind of simulations. And here on, and you can have a look at the results in this paper given here. So on the left-hand side, I show radial density profiles for the various components. So for the fuzzy dark matter only simulation that we already saw in the on the previous slide in green, and you can see that for all the shown redshifts here, the inner part can indeed be characterized by this soliton profile. Given here is the dashed black lines, and then then we have two other runs, namely fuzzy dark matter with baryons here in blue, and also an equivalent cold dark matter run, both with baryons. And you can see here the gas fraction, also the radial density profile, also in that graph here. And what we could show, interestingly, is that now including baryons, the soliton profile, the typical characterization is not a good fit anymore. You can particularly see that here in the two lower panels, that the blue line is not well fitted by the dashed black line anymore, but by this dashed red line. And that we obtained by finding the ground state solution of the Schrödinger-Poisson system, but now under the influence of the gravitational potential sourced by the additional component of the baryon contribution. So including this external potential from the baryons, we can then numerically find the expected ground state solution, and that here is the red line. So indeed, fuzzy dark matter, even with baryons, finds this ground state solution. It's just altered by the inclusion of baryons. And the second thing that we could show is here on the upper right panel. That's velocities for different redshifts in these three different scenarios, and for at three different radii, basically. So outer, meaning at the virial radius, central, meaning close to the soliton, and then actually the soliton here in represented with solid lines. And for the first, so this fuzzy dark matter only simulation, we see that all three velocities are constant over different redshifts, and also quite equivalent with each other. So here really the virial velocity at the virial radius is a good proxy for the entire halo velocities. But as soon as we include baryons, and that's independent of whether we look at cold dark matter plus baryons or fuzzy dark matter plus baryons, we see that these baryons actually heat up the central part, and that the soliton velocity therefore also increases if we include baryons. And that actually makes the ground state solution more compact, since higher velocities result in smaller de Broglie wavelengths. That shows up also in the ground state radius, and that we indeed see here in the radial density profiles, that with smaller redshift, the inner part becomes more and more compact. So this red dashed line becomes more and more compact. And then finally, we again had a look at the central densities of these ground state solutions, and again saw that they oscillate, and again took the power spectrum of that and found a typical frequency that again very nicely aligns with the free fall time of that ground state solution, where now again the free fall time being roughly 1 over the square root of the density is now altered by baryons, in the sense that this free fall time is now 1 over the square root of the sum of both densities, so the sum of the fuzzy dark matter and baryon densities. And the expected frequency range here is color-coded in orange, and we see that maximum power we get indeed in this frequency range. So that already brings me to the very recent results. Actually, by the time that we record this, it's not yet published, but hopefully by the time you hear about it, it will already be published. But this is really very, very recent work done in collaboration with Mattea and Richard from New Zealand, and then Christoph and Jens also here in Göttingen. And what we did is we implemented what we call Axion NUX, so an extension of the NUX code that can do now fuzzy dark matter dynamics as well. And with this code, we could now, for the first time, basically redo those quantifications, but now with mixed dark matter. So where we have fuzzy and cold dark matter alongside each other with varying fractions. So what is the goal of this code? So it's again adaptive mesh refinement simulations for mixed dark matter. The cold dark matter part we just evolved by the n-body scheme already implemented in NUX. So there we didn't have to do anything. And then for fuzzy dark matter, we implemented a spectral method on the root grid, which is periodic and uniform, and therefore a spectral method is the most efficient way to evolve the root grid. But then final levels are not periodic anymore, and therefore there we use finite difference method. And then the baryons that we didn't include in this simulation yet, but plan to do that in the future. There are already modules, at least for the so there's already a hydrosolver in NUX. So the part that is still missing is some baryonic feedback, and we have to finish the star formation routines. But so that hopefully will come in the future. But the mixed dark matter scenarios here I can already present. And here on the right-hand side, you see a typical result of one of our simulations where we quantified spherical collapse all the way into the nonlinear regime. And here we really see the strength of this adaptive mesh refinement, because here on the upper left, you see our entire simulation box with this tiny overdensity in the middle. But then this overdensity here is refined a lot, that you can see here in this right-hand picture. That's a zoom into this small central region, and you start to see the granular structure, and also the grid structure of our adaptive mesh refinement algorithm you can see here. And then zooming further into the very center of that mixed dark matter halo, here in the lower left, you can really see the interference pattern, and then also in yellow, the solitonic core that emerges in the very center. So that we want to now quantify and show the results in the next 2 slides. And here I want to start with the linear collapse first, because there we actually have analytic results, since it's a linear regime, and we can test our code. We indeed, you can have a look at the paper once it's out. We indeed have a huge test suite actually showing also the vast range of possible applications for that code. So we redid linear growth of a overdensity. We simulated a soliton and saw that it rings at the expected frequency. We redid the condensation simulations that Levkov et al. Introduced a few years ago, and all this, yeah, you can see in the paper all this worked very nicely. But here I want to really concentrate on the new results, and those will be spherical collapse of mixed dark matter with different fractions f. So here in the upper two equations, f really denotes the fraction of fuzzy dark matter that we assume from 0 meaning no fuzzy dark matter and pure cold dark matter, and 1 being pure fuzzy dark matter without any cold dark matter. And yeah, here you can see these familiar linear evolution equations for overdensities for fuzzy dark matter at the top and cold dark matter at the bottom, where the difference between both is that fuzzy dark matter has this K4 term that introduces the gene scale if those two terms cancel out, so the gravitational term and the gradient energy term. And then the dynamics of fuzzy dark matter is in addition sourced by the cold dark matter overdensity if we assume we have cold dark matter in the simulation, and vice versa. The cold dark matter evolution is also sourced by potentially by the fuzzy dark matter overdensity if we have that. So that's the linear equations. And actually for cold dark matter, this evolution has a analytical solution if we assume that there's no fuzzy dark matter overdensity. So if we set the right hand side to 0, then here at the lower left, that's the analytic result, that the overdensity, central overdensity scales proportional to a to some power. And indeed, if we set f to 0, so if there's no fuzzy dark matter, then we get the typical linear increase, so then that exponent becomes 1. And if we have the pure fuzzy dark matter case, so if we set f to 1, then this becomes 0, and cold dark matter cannot collapse. There's also no cold dark matter anymore, but it's increasingly suppressed. And that indeed we can see here in this left-hand side, on the left-hand side in this figure, where we show the maximum cold dark matter overdensity as a function of the scale factor, so a function of time, for varying fractions. So 0 in all the simulations that or results that I will show, 0 fuzzy dark matter is always denoted by the blue line. And then the more fuzzy dark matter we have, it will become more and more red. So here the dashed lines represent this analytical behavior, and the solid lines are our numerical results. And as we can see here, they basically perfectly align with each other. So apparently we get the linear regime right, and the expectations really meet our numerical results. And then additionally, on the right, I basically show the opposite picture, namely the maximum fuzzy dark matter overdensity now. And also here, the linear equations give this at least late time polynomial behavior. And again, the linear theory is represented here by the dotted lines, and our numerical results are the solid lines. So I should mention that for both of these simulations, I should have said that before, we are on scales below the gene scale. So fuzzy dark matter should not collapse, and therefore it suppresses the growth of the of cold dark matter over density actually. And also on the right, fuzzy dark matter cannot clump unless there is a gravitational potential source by cold dark matter. So it makes sense to initially only have an overdensity in the cold dark matter part and a homogeneous fuzzy dark matter part, and that is actually what we simulated here with the solid lines, and where we also gave the analytical linear expectation. So since we have a homogeneous field, we basically start at minus infinity, and then fuzzy dark matter starts to clump into the cold dark matter potential well, basically. And we see that indeed here again, the linear expectations are very much what we obtain from our simulations. Additionally, we show that this is not an artifact of our very artificial initial conditions by also initializing an overdensity in fuzzy dark matter, and that's the dashed lines. And since we are below the gene scale, this overdensity is unphysical, and indeed what we find is that it immediately disperses. So it first decreases in overdensity and then just oscillates around and cannot collapse until at very late time, fuzzy dark matter has collapsed sufficiently that it can overcome the gene scale of fuzzy dark matter, and then the late time behavior is again very much the same. So that is all very nice and consistent. So now let me come to the interesting part actually, which is now the strongly nonlinear regime. So if we let our halo further collapse and virialize, and these are now final results for different fractions of fuzzy dark matter, here always seen in each plot. So F at radial density profiles here on the right for different fuzzy dark matter fractions. And these results are for the basically the final radial density profiles that we obtain after slightly more than four free fall times, so long time after virialization of that mixed dark matter halo. And the interesting thing is that you can see that at least in the outer part, so on super de Broglie wavelength scales again, that the cold dark matter profiles in blue are basically identical to the fuzzy dark matter profiles in red. If we rescale the two profiles by the ratio, by the fraction of fuzzy dark matter. So if initially we had, for example, here in the very top, initially we had 1% fuzzy dark matter, then also within that fully nonlinear collapsed halo, this initial fraction of 1% is still there. And for example, here for a fraction of 50%, so identical proportions of cold and fuzzy dark matter, we can indeed see that it's basically on top of each other and indistinguishable. And on the other hand, coming to the velocity profiles on the left, we also see that the characteristic velocities both for cold and fuzzy dark matter are almost independent of the fraction of fuzzy dark matter. So we always see a characteristic velocity for this halo of around 20 kilometers per second or so. So it's pretty much independent of that. And these two results together again show that the Schrödinger-Vlasov correspondence also holds now for this mixed dark matter scenario, so that the evolution of cold and fuzzy dark matter is indistinguishable from each other on super de Broglie wavelengths. That has the interesting consequence that if you want to look at, for example, heating or cooling due to this granular structure, or condensation of this ground state solution in this granular structure or things like that, that typically depend on the effective mass of the granules. So namely the volume of each granule multiplied by its characteristic amplitude. And all these analyses that already partially have been done in the past, you can immediately apply to the mixed dark matter case just by rescaling the effective granule mass by the fraction of fuzzy dark matter that you assume. But you don't have to redo all the calculations, just rescale the effective granule mass by the fraction of fuzzy dark matter, and you're immediately done. And can redo all the calculations that you did, for example, for heating and cooling of star clusters like Eridanus 2. So that was something that Jens Niemeyer and Doddy Marsh had a look at, and so on. So all these things can immediately be redone for mixed dark matter. And then finally, the other interesting thing here is that for a lot of fuzzy dark matter, we again find ground state soliton solutions in the center, here characterized by the black solid profiles here. You can see they perfectly fit to the fuzzy dark matter inner profiles, but only for sufficiently much fuzzy dark matter. So as soon as we have 10% or less fuzzy dark matter, then the cold dark matter dynamics are so dominant that fuzzy dark matter cannot build a ground state solution. I mean, that's only roughly, but around 10%. So if you assume less than 10% fuzzy dark matter, then you can probably not assume that there's a soliton in the center anymore, or at least it fluctuates a lot. You can still see that the inner part is suppressed, so there's still a core as opposed to the cold dark matter cusp, but it's not well fit by a soliton profile anymore, and also not well fit by the modified ground state solution that we used for the baryons. And you can see here that it fluctuates a lot. So there's really no stable ground state forming for too few fuzzy dark matter. Finally, the solid vertical lines here, that's the viral radius just for reference. And the dashed vertical lines represent the core radius, traditionally defined as where the central density has dropped to half its value. And interestingly, if we use this core radius, then Philip Mosch actually has shown in his really cool paper on boson stars and turbulence a few years ago that this typical length scale for solitons can be identified to a typical velocity for solitons with this numerical factor of 7.5. And this characteristic soliton velocity is shown here as the dashed lines on the left in the velocity profiles. And you can see that indeed these dashed lines very nicely align with the peaks in the fuzzy dark matter velocity profile. So we indeed see that this characteristic soliton length scale is associated to the characteristic velocity, soliton velocity. That you can also see here in the lower left panel, where we show the peaks of fuzzy dark matter in the fuzzy dark matter velocity spectrum with these diamonds, and the peaks in cold dark matter by these crosses. And the black solid line here is the prediction from Philip. And we see that indeed the peaks in the velocity spectra for fuzzy dark matter very nicely align with this curve. And then cold dark matter at least tries to follow this velocity evolution. And the dashed line, the horizontal dashed line, that's the viral velocity. So what we see here, interestingly, is that if there's no soliton forming, so that's the blue symbols here, that's very few fuzzy dark matter, then the typical velocities in the center of the halo are very close to the virial velocity again, so something that we expect. But as soon as we have sufficient fuzzy dark matter to form that soliton, then especially the peaks in the fuzzy dark matter spectrum deviate strongly from that virial velocity by, in the most extreme case for pure fuzzy dark matter, by a factor of 3. And that will also alter the core halo mass relation that assumes the equivalence of the virial velocity and the soliton velocity. So that will be altered by up to a factor of 3 or so, making the soliton heavier than expected. And finally, we can look at the growth of that soliton, and that's what we do in the two upper panels. Here on the left, we show the maximum fuzzy dark matter overdensity. So that's the central core density as a function of the scale factors, as a function of time. And what we can see is that initially, indeed, there's for all the fuzzy dark matter fractions that we get this degenerate evolution, again showing that fuzzy dark matter and cold dark matter are degenerate on super de Broglie timescales. So here, this degenerate evolution until a certain time, which corresponds actually to roughly 1.5 the freefall time. So basically at a time of virialization and just after collapse. And then we see that especially for a lot of fuzzy dark matter, a soliton forms, and that strongly increases the central density by a few orders of magnitude, 3 orders of magnitude or so. And we can see that especially for a lot of fuzzy dark matter, the increase is stronger, and the fewer fuzzy dark matter we have, the fewer the increase, and then for almost no fuzzy dark matter, there's just no soliton forming, and therefore we don't have any increase here in this virialized halo. And we can analyze that slightly better. I probably put that down here. On the right-hand side, which is basically the same, but just represented differently. So now we have the maximum fuzzy dark matter amplitude, so the square root of the density, and we use a linear scale here for the y-axis, and we parameterize it by the freefall time. And but other than that, it's basically the same plot, just represented differently. And what we see here is that after, as I said, 1.5 roughly freefall times, we have this formation of the soliton. And as was already shown by Levkov et al. In their condensation paper, we again recover this linear increase in the amplitude, and that we show here by these equations. So that's the linear increase in time of this amplitude, and indeed it increases linearly with this condensation time. So that's a formula that I took out of this Levkov paper. And putting in the soliton velocity and the central density, we get a typical soliton time, and we see this linear increase over soliton time. And we see that for more fuzzy dark matter, this time scale is shorter, therefore we have a stronger increase for larger fractions of fuzzy dark matter. And interestingly, even though we are already at velocities a factor of up to 3 larger than the virial velocity, we don't see any slowdown in the growth of that soliton. I mean, that's something that would definitely be interesting to have a look in the future, to let those simulations run further and see at what time there is a saturation. But now here in these simulations, even with velocities a factor of up to 3 higher in velocity, we nonetheless don't see any saturation yet. So that is definitely something that is interesting to have a look at in the future. Okay, so that brings me to my quick conclusions. And so basically at the beginning, I said that fuzzy dark matter structure formation is similar to cold dark matter on super de Broglie wavelengths, with the exception of this initial cutoff that, for example, can be probed by Lyman alpha, and that excludes masses smaller than 10 to the minus 21 eV. But as soon as you have slightly heavier masses, then deviations are on the strongly nonlinear regimes in collapsed structures of filaments and halos. And then here really the distinguishing features for these masses, fuzzy dark matter masses, are the strong stochastic density fluctuations in halos and filaments on the de Broglie length and time scales, and the formation of stable oscillating solitonic cores that don't have any analog in cold dark matter or warm dark matter scenarios. And then finally, this the local fuzzy dark matter density would also be interesting or very important for experiments that assume a certain background of axion dark matter, for example. And then, as I said, heavier fuzzy dark matter masses of around 10 to the minus 20 or so eVolt are then best probed and constrained by on these nonlinear galactic scales by solitonic oscillation mergers, by gravitational heating and cooling due to the interference pattern, tidal disruption, and so on. So that really shows why also in the future we need further dedicated fuzzy dark matter simulations, especially on these scales, and that's something that I will definitely further pursue in the future. So thank you very much for your attention.
Thank you, Bodo, for that excellent talk. Let's all give a virtual clap. And I have 2 questions for you. So first of all, very excellent and nice talk, and I learned a lot. And you've introduced these mixed dark matter models with fuzzy dark matter and cold dark matter. And I was wondering if you could discuss a little bit the motivation for these mixed models.
So I mean, these fuzzy dark matter masses, these ultralight fuzzy dark matter masses of 10 to the minus 20, whatever, typically are motivated by the Exiverse coming from string theory anyways. And if we have that Exiverse indeed, then there's naturally not just a single axion-like particle, but a range of axion mass of axion-like particles on a logarithmic mass scale. So there would be naturally a few particles that are probably lighter than would be needed for cold dark matter at all, and then once their de Broglie wavelength is above the Hubble scale, then they would contribute to dark energy, and then there are probably heavier ones, and their de Broglie wavelength would be on scales that are not on the scales that we simulate. So those would naturally contribute to cold dark matter, and there could be then one axion that is on this mass scale of 10 to the minus 20 or 21 electron volts, and then that would result in all that all the results that I showed would form hopefully this solitonic core and the granular structure, but it would be in the case really of mixed dark matter that most of the axions probably then contribute to cold dark matter, but we can distinguish that scenario from pure cold dark matter by that one or maybe two light axions that happen to be on the interesting mass scale of around 10 to the minus 20 electron volts. So that's basically the main motivation. And on the other hand, that small window that we still have is also rapidly closing. by more and more dedicated simulations and better observables. So probably in the near future, we will know if fuzzy dark matter can actually contribute 100% to the dark matter, or whether that's excluded in the next few years, and also that then drives interest, I think, in mixed models where you can probably then alleviate those constraints a little bit and go to masses that are constrained if you have this pure fuzzy dark matter case.
Excellent. I have one more question. So you've discussed these beautiful three-dimensional simulations of radial collapse, but because you have 3 dimensions, you start seeing some granularity and especially with the AMR applied to the mesh. But you've described 2 types of structures: the soliton and superposition of waves with the Maxwellian velocity distribution. And I was wondering if there might be a third type of feature present, which is hard to tell from the density distribution alone, but easier maybe with the frequency. So these are these higher order states that you solve for when you impose the gravitational potential in the Schrodinger equation. So first you have to, and particularly I was wondering whether that might be the case in the simulations with the large cold dark matter fraction, where you had those large, you had a compact core that was more compact than the soliton, and you had these large oscillations.
Yeah, no, that's a very interesting point. We didn't investigate that yet, so I cannot say for sure, but it's definitely an interesting idea to explain why there's no stable soliton forming for these very low fractions. So maybe indeed these strong oscillations that we saw in these low fraction simulations is indeed due to the interference of multiple ground state solutions with different n whatever number of nodes.
Oh yeah, these higher order states. Yeah. Okay, and then
that's something that
thank you.
Is interesting to investigate, but yeah, we didn't do that.
And the left Cobb formation time scale for a soliton core is just larger than the time that you've simulated this collapse for those cases.
Or maybe that too. I mean, yeah, we saw that this formation is strongly suppressed for small fractions, and that indeed could be true as well. So I think there it's really the time scale for the formation is just, as soon as the time scale for the formation is larger than the typical time scale for the cold dark matter dynamics, then there's probably no way that the soliton can form. But yeah, you're right. We would probably not even have seen it because we didn't simulate it long enough. So yeah, that's one of the 2 reasons.
Okay. Thank you very much, Bodo.
Yeah, you're very welcome.
And let's give a round of applause again. Thank you.
Thank you.